second lecture of theory.
Thank you very much. Thanks for coming back. So we are in the second part of this lecture. So it is chapter 2, a viscous vortex in an external flow. General title of this lecture. And what we did yesterday, I tried to convince you that it was a good idea to study the following model equation, dt omega plus u plus f dot gradient omega equal to nu Laplacian of omega. So this is for x in R2, for t positive. This is the equation I call Vf, the vorticity equation with an external Vf. And the idea is that in this equation, u is the velocity field produced by omega by the Biot-Savart law, and f is given. F is the external field, which is given, satisfy nice bounds, is smooth, is divergence-free, and this is supposed to represent the velocity field produced by the other vortices in the flow typically. Okay? So I started mentioning some results about this equation. So the first one was my proposition 1, saying that the Cauchy problems for this vorticity equation with an external field F is globally well posed in the critical space L1 of R2. So for vorticities which are just integrable. And to be completely honest, I know nowhere what this proof is explicitly written, but it's written explicitly when f is equal to 0. This is basically the results by Cato in the 80s, Benarzi in the 90s, and so on. And adding a lower order term with some smooth given external field doesn't change any of the arguments. It will change the behavior of the solution, but not the existence and uniqueness of the solution. So I will take this for granted. Okay. Now, of course, if you assume more on the initial data, you have additional properties of the solution. So a little remark that I would like to make regarding the center of vorticity. If in addition you assume that 1 plus x omega is in L1, so you have more decay at infinity with a wave, then 1 plus x omega e stays in L1 for all t in my existence interval. I remember that I was given a velocity field phi, which exists over a time interval 0 to capital T. I could take capital T is equal to infinity, but let's say capital T. So for me, global well-posedness is up to the time where the equation is defined, which is capital T. And we can define what I call the vorticity center, the vortex center. Center of vorticity, say x bar of t, is 1 over gamma integral of R2 of x omega of xt df. Here, gamma, I recall, is the integral of R2 of omega of xt dx. And I assume that this quantity is non-zero. Okay. I will typically, the reason to consider this model was to focus on a given vortex. So I assume that this quantity is non-zero and up to symmetry. I can assume that this quantity is positive. Okay. Otherwise, I make some symmetry of the space. Okay. So now I can consider the center of vorticity, which is given by this formula. And now there is a lemma, which I mentioned already yesterday, but I didn't prove, is that for all t in my time interval, I can compute the velocity of the center of vorticity, and I find the corresponding formula, which tells you that this is the average of the vorticity distribution omega of x. So this was the average of the position x. This gives the location of the center of vorticity, and now the speed of the center of vorticity is given by the average of the external velocity field on the vorticity distribution, that is solution of the equation. So I promise to prove this. So we start with proof. Okay, so we'd like to differentiate this formula. This is possible at least if t is strictly positive because the solution is smooth for positive times, parabolic smoothing. So for t strictly positive, we can compute. So take it for granted that I can make this calculation at least for t positive, 1 over gamma, integral over r, x, and here I have to replace omega by dt omega from the equation. Okay, so dt omega is mu Laplacian of omega minus u plus f dot integration omega. Okay, and I have to compute the various terms in the right hand side. So this is not difficult at all. So first the Laplacian integral over R2 of x Laplacian omega dx. This is obviously equal to 0 because we integrate by part twice, and we have only one x, so this is still by the Laplacian. This gives. Okay. Now, what about the advection term here? So minus integral over R2 of u plus x here, x u plus f dot gradient omega x. So this is the term that remains. You use the divergence precondition, so the integral of R2 of x, divergence of u plus f x, and then you integrate by parts to kill the x here, and you obtain, not surprisingly, integral of u plus f times omega dx. Okay? And whatever contains f here is the result that we would like to obtain. Okay? But there is a term, the self-interaction term with u. And this one is 0. So the last argument in the proof is that the integral over R2 of u of x, omega of x, dx, will be 0 when u is the Biot-Savart of omega, when u is obtained from omega by the Biot-Savart law. So the simplest way of proving that is just to plug here the formula for u of x from the Biot-Savart law. So this gives you 1 over 2 pi, integral over R2, integral over R2, x minus y orthogonal over x minus y modulus square, omega of y, omega of x, dx, dy. So you obtain a double integral. The first integral was here. The second integral comes from the fact that I replace u by the integral representation in terms of omega. And now this is 0 because you see that the integrand is odd with respect to the permutation of x and y. If I exchange x and y, this doesn't change here. But here, since the Biot-Savart kernel is odd, then you have a minus sign, so which quantity is 0. So we obtain exactly that formula here, at least for positive time. And now this is a continuous function of time all the way up to 0. So certainly it's differentiable all the time, and you have the continuous component. Yes? Okay, this is defined for t strictly positive. So for t positive, you will have omega in L1 intersection with L infinity. So u will be in all LQ spaces with q larger than 2 points. It's not in L2 because of the exercise I gave yesterday, but it's all in all higher Lebesgue spaces, and there is plenty of, this is largely sufficient to justify this calculation. Good. Okay, so this is the equation for the center of. So here's the calculation showing that the self-interaction has no influence on the location of the center of vorticity. I used that yesterday to derive the one function. Okay, so now this is not exactly what we want to do, okay, because we want to consider measures as initial data. We'd like to start from a Dirac masses, and this we discussed yesterday. So for the moment, we are in L1. L1 is a nice framework, but it does not contain Dirac masses. So let me just mention measures as initial vorticity. So which kind of measure can we allow? Let me make a little digression on the space of measures and the relation with the 2D vorticity equation. So denote first notation, M of R2, the space of finite signed random measures on R2. So I have a lot of words here, finite, signed, and random, which I should briefly explain. Okay. These are the measures we consider. So it's our measures on R2. So signed means that they are not necessarily positive. I mean, when you do probability theory or integration theory, you consider only positive measures typically. But here the measure is my initial vorticity, and the vorticity can be positive or negative. I mean, you remember the blue vortices and the red vortices. So I really need to have a signed measure, which is value, which can take positive and negative value. Now, what is finite? What is random? Random is just that this is a regular measure. I don't allow the counting measure or something like that, something that can be realized at the dual of continuous functions, okay? So it's just a regular measure. Now you have the Jordan decomposition. So if mu is in this space here, we have the Jordan decomposition of the measure, which is mu is equal to mu plus minus mu minus, where mu plus and mu minus are positive measures. So this decomposition is not unique because you could add a positive measure here, and they would cancel in the difference. But there is a unique way to make it so that the support of this measure are essentially disjoint. Okay. So this is a positive. There is a notion of positive part of mu and negative part of mu, just as for functions. Okay. This is called the hard decomposition of measures, but I don't do a course on measure theory. Okay. So you have this. We denote. So then we denote absolute total variation of mu, which a measure which is mu plus minus mu minus. So you take sort of the absolute value of the measure mu by taking the sum of these, and we introduce a norm which is the total variation norm of mu, which is just this total variation measure of R2. And this we say that this should be finite. So mu plus mu is a difference of the positive and the negative measure, both of which are finite in the sense that the measure of the whole space is finite. This is what we call by this space M of R. Okay? So why do we consider this space? Because there is a result saying, which is a proposition 2, okay, which says that the Cauchy problem for this, well, to be honest, again, this proposition has been written for f is equal to 0, but I claim it's the same for f non-zero. The Cauchy problem for Vs is globally well posed. In the space of finite measure. So not only you can solve with L1 initial data, but you can go to the space of measure. So I should comment a little bit on this result. It goes in a direction which is not what I want to do in this lecture, but still I will start with a Dirac mass, so I'm using a particular case of this theorem. So examples. So first of all, why do we consider these measures? Is this just for generalizing, or is there something interesting for fluid mechanics? So examples of non-smooth initial data. Okay, so within the category of measures, we have a lot of examples which are interesting for fluid mechanics. So in increasing order of singularity, here's the typical list. So first element of the list is absolutely continuous measure. Okay, so we could get it simple. You assume that your measure is just some omega x with omega with an L1 of R2 density. Okay, If the measure is absolutely continuous with respect to Lebesgue, there is it's the Lebesgue measure times some L1 function. And in that case, you are back to proposition 1. This, of course, the measures contain the absolutely continuous measure. So the L1 case, what is contained? So examples is what is called a vortex patch. Vortex patch, which means that omega typically, it could be the indicator up to a constant, the indicated function of some domain omega, and omega is a smooth bounded domain. Now, we consider a vorticity which is 1 inside the domain, 0 outside. It's not very regular, but still it's L1. And you consider the absolutely continuous measure associated to 1. This is a vortex patch. Okay? So vortex patches are being studied. These are very important flows for to the Navier-Stokes or Euler equations. Okay, now you could have singularly continuous measures. Singularly continuous measures. So, for instance, you could have a vortex sheet. It is more singular. This is, for instance, a measure that is supported by a smooth closed curve. Okay, so you have now a curve, for instance, like that, and you assume that the velocity vector has a discontinuity along this curve, which leads to a measure which acting on a function test phi, would be something like, if this is a curve C, the integral of C of phi EL, something like that. This is a measure that is supported, which is singular. I mean, it's singular with respect to Lebesgue measure because it's supported on a curve which has 0 Lebesgue measure. Okay, and this models vortex sheets where you have a discontinuity of the vector field along a curve. And this is well known because it gives rise to the Kelvin-Helmholtz instability for Euler and things like that. For Navier-Stokes, no problem. You can take this as initial data because this is contained in my space of measure. And finally, there are point vortices. Is the measure to be a finite infinite combination of Dirac masses located at some position with some coefficient. So this is the, you could have vortex patches, vortex sheets, or point vortices, and this is sort of the catalog of non-smooth initial data you may consider for 2D flows and which have physical relevance. And the nice thing is that this space M of R2 contains all of them. This is in increasing order of singularity because here the velocity field is, say, log Lipschitz, if the patch is smooth. For vortex sheets, it's discontinuous and bounded. And for point vortex, is unbounded. It has a 1 over x singularity near the origin. So we see clearly that we are in increasing order of singularity. Now, okay, what happens if you want to solve, okay, if you want to solve the vorticity equation with such initial data, what can you do? Suppose first that you have, in the case f is equal to 0. So, Cauchy problem. I should give some references for f is equal to 0, which is the usual vorticity equation. Okay, so to solve proposition 1, I told you very briefly at the end of last lecture that you can do it by a global fixed point argument on the integral equation. You write the integral equation and you make a fixed point argument using the same space as in the Fujita Kato, and things like that. Okay. This works. Does it work for the measures? Okay. So it works, but there is a condition on the initial data. When you make a fixed point argument, there is always a smallness condition somewhere. Depending on the space you start with, you can achieve the smallness condition by taking the initial time, the time on which you construct the solution sufficiently small. But in critical spaces, which are exactly scale invariant, you cannot do this trick typically. So at some point, you have to impose some smallness condition on the data. And it's very interesting to see what it happens here. So the main remark is that the fixed point argument gives global well-positness for omega 0 in the space of measures if you have a condition, and this condition is the following one. You take your initial measure, omega 0. Whatever is absolutely continuous in your measure, no problem, because you know for proposition 1, there is no problem. Whatever is the singularly continuous part of your measure, no problem. But the problem are the atomic part. The measure can have Dirac masses, at most a countable family, because it's a finite measure, and see that a finite measure has at most a countable collection of Dirac masses, okay? The coefficient of which form an L1 sequence, an integrable sequence, a summable sequence. So you take the atomic part, omega 0. Okay, I have a problem with this notation, omega 0. Let's say mu for the measure. So you take the pure point part, which is just the atomic part, only the Dirac masses in the measure, and you take the total variation norm. So this is a quantity which should be smaller than a universal constant times the viscosity parameter. So this is exactly what the fixed point argument gives you. You take the total variation norm of the atomic part of the measure. So in there you consider the large Dirac masses. You consider this quantity here. So for a measure like this, in that case, if you take mu total variation norm, it's just the sum from 1 to n of the modulus of this gamma I. Okay, just this, no more complicated. So you take the sum of the absolute values of the Dirac masses. You divide by viscosity. This is a dimensionless quantity, like a Reynolds number, and this quantity should be smaller than some universal constant that you can estimate in the argument. Okay? And if this is true, the fixed point argument gives you immediately a global solution. And in particular, this works in the case of proposition 1 because there is no atomic part in your initial measure. If this condition is violated, the fixed point argument gives you nothing. No local existence, nothing. It's like in all these results in these ultimate scale invariant spaces, like the Korf-Tatarus theorem, you have global existence for small data and uniqueness. For large data, you have nothing. Okay? To have a local well-positness for large data, you must use a space in which the smooth functions are dense. This is not the case in the space of measures. The smooth functions are not dense. You cannot approximate in the norm of the space the Dirac masses by smooth function. Okay, so here you need a wall. I mean, should remove this condition because this assumption is exactly what we don't want to impose. That impose that the Reynolds number is small, and I will never see the motion of my point vortices if I assume small Reynolds number. So I need exactly to go beyond this theorem. Okay, so this is possible, and let me give you some references. Okay, so there. Okay. So references. So the first point is justifying what I said, that you have a global well-positness under these assumptions. And this was shown by Cote. This is not a well-known paper, but Cote is my colleague of mine in Grenoble, so I have certainly to quote him. There is a paper by Giga, Miyakawa, and Ozada, first published in 1988. And there is a paper, one of the last paper by Kato, 1994, which is devoted to that. So in these papers, you find global, you show existence for all data and uniqueness under this condition. You can prove existence because existence can be proved by approximation. If you start with initial data which are non-smooth, you can make it smooth by some regularization procedure, for instance, by applying the heat kernel for small time. And then you prove the existence of a global solution by proposition 1, and then you pass to the limit. So proving existence of some solution is not a big deal, but uniqueness, you really need the smallness condition of the fixed point argument. Okay, so after this work here, what remains is the case of large Dirac masses. So one large Dirac mass, which is what we need for today's lecture. So this is a result by me and Jean Wayne, and it's 20 years ago, I'm afraid. And for the general case, combining, well, we prove an argument which tells you that for a single Dirac mass, you have a unique global solution, which is, by the way, the Lambo-Zane vortex, which I recall. And we show that this is unique, which is a general class of solution. And the general case, this is Isabelle Gallagher and me. And this was the same year. In fact, there is also a paper by Bedrosian and Masmoudi. The first paper by the dream team based on Bedrosian and Masmoudi, which was published in 2014, is also devoted to this problem. Now, of course, this pair has been known for much more serious works, but the first thing they did together is something about global well-posedness of the two-dimensional vorticity equation and some other equations. So we know in the case of no external field how to prove global existence and uniqueness for all measures without any smallness assumption of this kind, but the uniqueness proof is not done by a fixed point argument, or it's done for a fixed point argument, but after some preparation, not directly on the equation. Okay, so in what follows, I will sort of take for granted that proposition 2 is true. Is always, it has not been written, but again, none of this argument changes drastically if you add this lower order term. And this lower order term will change qualitatively the behavior of the solution, which we want to study, but certainly for the question of existence of uniqueness, this lower order, I mean, you can always treat it perturbatively. Okay. Okay, so in what follows, in all the rest of this lecture, or at least today and tomorrow, in what follows, we consider this vorticity equation with an external field with initial measure omega 0, which is a Dirac mass located at some point Z0. Okay, so gamma will be strictly positive, and Z0 will be some arbitrary point in out. So I would like, so this I justified yesterday. I consider one single vortex in an external field. So I take one single Dirac mass. And the reason I start with a Dirac mass is because if you start with a Dirac mass, you have zero extension. You cannot be deformed by the velocity, the external field, because you have zero extension. And then the vortex grow directly in the interacting picture, taking into account the action of the external field. If you take other initial data, you will have some boundary layer in time and some more. So it's a two-step process. If you want to consider, first, you should consider the idealized case, which is this one. And then you show that how other initial data relate to this ideal case that we have. So these are my well-prepared initial data, and this is my starting point for studying the equation. Okay. Yes?
Yes, so maybe it's gonna be vague. But so there are those critical spaces.
Yes.
In which, and the other ones are where smooth functions are not dense. Where to close the fixed point, you have to impose a smoothness.
Yes.
So for instance, you said
Cortataru, yes. PMO minus.
PMO minus.
Yes, exactly.
I mean, a priori, to me, PMO minus 1 is as bad as measures.
Yeah, it's comparable, yeah.
However, in BMO minus 1, the uniqueness has been disproved.
That's true. But
so what's the difference? Like, do you have any guess if there is any difference between measures?
Well, I mean, each case, I mean, this BMO minus 1 was 3D, of course, okay. Here, in the particular case of measures, unique pairs can be proved. So, I mean, this space is better. It's better in the sense that the way you can I mean, whenever this condition is, this smallness condition is satisfied, you are okay. Okay. But the only way you cannot satisfy this condition is just because of a few Dirac masses.
So the pathology is such an easy thing to handle.
Exactly. You know exactly what is the defect of this space, and you can cure it by explicit treatment of these cases. This is what we did. In BMO -1, the defect is due to, I don't know what, a full part of the space, which is okay. So here, this is what is nice with this measure space in 2D, is that the only obstacle to the fixed point argument is, say, a finite number of large Dirac masses, and this you can treat explicitly. So, yeah. Yes? Well, I mean, it's 3D. It's not scale invariant in 2D then. You should adapt it. Yeah, it's for velocity. Yeah, so it's okay. Scaling change a little bit with the dimension. Good, okay. So let's go back to what I really want to do. So, okay. Each time I move, I have to. Now we'll start to state the main results, at least the main result concerning well-prepared initial data. But for this, I need to introduce, some relevant physical quantities related to the problem. I'm sorry, it's a little bit boring, but it's really helps understanding the result, and it's not because we are solving theorems that we should be exempted of writing things that are physically relevant, okay? So the first quantity is the Reynolds number. There is a Reynolds number in this problem, and it's given by, say, Reynolds number. I define it as the ratio gamma divided by mu. So the circulation gamma, the unit is meter square per second, and the kinematic viscosity, the same unit, meter square per second. So when you take the ratio, this is a dimensionless quantity, which I define to be the circulation Reynolds number. And this quantity, I will assume, is large. Large means that advection is dominant over diffusion. This will have a very large effect on the solution we consider. If I consider the converse regime where the Reynolds number is small, it means that diffusion is dominating. So the vortex will get spread by diffusion without having time to move under the advection of the velocity field. It will just spread everywhere. This is a diffusive regime with small Reynolds number. This, by the way, would be satisfied in assumption. Now, the high Reynolds number, which violates this condition, is exactly the contrary. The vortex will move a long distance, a little bit like a point vortex, before getting really large, okay? So we really need this to have the separation of time scales to sort of see the vortex dynamics. The video I showed you is for high Reynolds number, otherwise you don't see what you see on the video. So I will define a small parameter delta to be just the inverse, which is mu over gamma, and this less than 1. So the first important parameter, everything should be for delta small in what I'm saying. Okay. Now, characteristic time. We impose an external velocity field. With this velocity field, there is some time associated with it, and there is also some length scale associated with it. Whenever we give an external velocity field, we in fact specify, we break the dilation invariance of the equation, so we specify a time and a space. So what I can call the characteristic time, it's I define the inverse of it, 1 over T0, and this is the cube of x in R2, cube of T in 0T, whenever the external field exists, of some norm of the Jacobian matrix of the first order differential, df of x. So I take the Jacobian matrix of F, so the differential of F. I take some norm of it, and I take a sup in X and in T, and this is the inverse of a time, so I define it to be 1 over T0. So do you have any intuitive meaning what this T0 is? This is a question for people doing ODEs. Well, this is the characteristic time of separations of nearby trajectories. 1 over T0 is a Lyapunov exponent of this velocity field. If you take two trajectories of the velocity field with nearby initial data, the initial distance will be amplified by something like e to the t over capital T0 in the worst case, and this is a T0 which gives this characteristic time. Okay, so it's a characteristic time of separation. It's a natural time interval related to the external velocity field. Okay, so our goal will be to control the solution at least until T0 and maybe up to a multiple of this T0, so while we see really something occurring. If the velocity field is created by another vortex, this is also more or less the time or rotation of one vortex around the other. So it's a characteristic time where you see some dynamics in the point vortex system. If your result for much smaller times, you don't see anything interesting. So we should reach this time T0 or maybe a multiple of this T0 at least to see something reasonable. Okay. Now there is something much more difficult to explain, which is the effective size of the vortex. To be honest, we hesitated a lot because we need a unit of distance, and the definition of which there are several possibilities, but finally we found that this one is the most natural. I take D is equal to square root of gamma times T0. So this I have to explain. Why do we produce this characteristic? This is an X, by the way. Meter squared per second multiplied by second square root is a meter. So it's a distance. But why is it the characteristic size of the vortex? Let me explain this rapidly. It's necessary to understand what we do. So what is the situation we consider? We have a vortex in an external field. Now, okay, let me make a picture, which is just a card. The question is, the velocity field of the fluid is the sum of the velocity field of the vortex and the external velocity field. The question is, which one is dominant? Which one is long? Well, it depends where you look at the velocity. Near the vortex is dominant because we'll see that the vorticity will be something like gamma over nu t or something like that. So it's very large near the center of the vortex. Very far away, the influence of the vortex is decreasing. So this is the external velocity field, okay? So you have this picture like that, you have the external velocity F, that, and in a region, in a disk of radius d, some d, near the vortex is dominant. Let's compute this d. What is the velocity field of the vortex? Well, it depends on the shape of the vorticity, but let's take just the computation from the point vortex. So u of x, suppose that the center at the origin to simplify the calculation is something like gamma over 2 pi x. It's defined like 1 over distance to the origin with the factor of gamma over 2 pi. Okay, this is the calculation of the point vortex. Okay. So if you take the deformation, I mean the Jacobian matrix, it will be something like gamma over 2 pi x squared. So the strain of the velocity field decreases like 1 over the distance square when you go away from the center of the vortex. At which time does it become more or less equal to the strain of the exterior field? The strain of the exterior field is 1 over T0 by definition. This is how I define it. So I say that this should be graphically equal to 1 over T0. To solve this equation, you find x is equal to d, where d is square root of gamma T0. So this is a region in which the velocity field is mainly due to the vortex. The influence of the velocity, the exterior field is relatively weaker. Whereas in the exterior region here, this is the external velocity field which is dominant. So it's very simple. So this defines sort of an effective size of the vortex. Warning, this should not be confused with the size of the vortex core. The size of the vortex core is due to the vorticity distribution inside the vortex. Here we can even take a point vortex for this calculation. And the size of the vortex core is 0, so it's certainly not equal to this one. Okay? So this is also important. It is size of the vortex core. And here, of course, since we start from a Dirac mass here, and we use, say, the heat equation, this becomes a Gaussian vortex with size square root of nu t. So this is square root of nu t, which is the diffusion length. So the diffusion length is much smaller, so we should imagine that inside this circle here, maybe we didn't take so long, inside this vortex here, you have some vorticity distribution, which is of size typically square root of nu t. Okay, so this is the vortex core where you really have the vorticity. Okay, and this is the sphere of influence of the vortex, which is something different. And the ratio of both distance is what we call the aspect ratio. So the aspect ratio, very important parameter, epsilon of t, is square root of nu t divided by d. Okay, it will make the ratio of the inner core of the vortex to the distance d. And this quantity will be much less than 1. Because if you take the square of it, epsilon square of t, you see that this is nu t over d square. But d square is gamma t0. Okay, gamma t0. You see that this is my delta, mu over gamma, times t divided by t0. So as long as t remains approximately of the order of this t0, which is a reasonable assumption, epsilon square is approximately my delta. Delta is equal to epsilon square. So I have a small parameter delta, the Reynolds number, the inverse Reynolds number, and my aspect ratio will also be small because of this calculation that we'll use a lot of time. Okay, these are all the relevant quantities I need. Sorry for introducing all that, but they will appear in the statement of the results. So you should keep them a little bit in mind. Maybe I should write them on some of the blackboard.
Yes, if I understand correctly.
Sure.
So in some sense, you are saying this D is the distance over which the vortex is dominating
yes.
over the
External.
But so you don't know if this external flow. So in principle, this external flow could be very large also inside the vortex because you are taking super of the air there. So that super
yes.
principle could be.
Yeah, but if the
okay, yes.
It's not a problem. If the velocity field is very large everywhere and so on, this means that T0 is small. So the sense the region, this will change the region where the vortex is dominant. So
right. Yeah. The worst case is when it is in the air is achieved inside this form. Yes.
But this gives me the opportunity of another comment. Again, suppose that the velocity field F is created by some other vortices. This D you can compute. This is typically the distance to the next vortex. So in case of interaction of vortices, there is no problem defining the D. You take the minimal distance to the other vortices. Okay. In an external field, it's a little bit more difficult to define, so that's why we did that. But in the case of vortex interaction, this D can be defined just to the distance to the next vortex. And this is, of course, a definition everybody agrees. Okay, this is. So then this aspect ratio being small means that the vortex core should be small compared to the distance to the other vortices, which means widely separated vortices, which is what we've seen in the video. Okay, now if everybody is ready, I can state the main results. So and the statement will involve some of these quantities here, okay? But now in a very simple way. Okay, so assuming proposition 2 to be true, so that I have a solution, I can state the first main result, which is theorem 1. So there exists, so say first, fixed gamma strictly positive and Z0 in out. I consider fixed initial data. I fix also the external field. The external field is given, the initial data are given, and now I make the statement. Okay, this should not be touched. You give yourself external field, you give yourself your initial data with a circulation and an initial point. Now, there exists constants K0 and delta 0, positive constant. K0 should be large, delta 0 should be small, such that if you assume that my parameter delta, so the mu over gamma, is less than delta 0, so I'm sufficiently high Reynolds number, the solution of my vorticity equation with an external field F, with initial data so omega 0 is gamma delta of 0, satisfies the following result. So 1 over gamma, integral over R2. I take my solution at time t, omega x t, and I compare it with what? With the Ozane vortex, self-similar solution of the Navier-Stokes equation. I will show you, recall what it is, centered at some position. So gamma over mu t, say omega 0 of x minus z of t over square root of mu t, okay, dx. So the difference between the solution and this approximation here is less than k0 times my epsilon, so square root of mu t divided by d. This is for t between 0 and capital T, where, so I have to explain a few things. So z of t, z is the solution of DODE, z prime of t is f of z of t, t, where z of 0 is equal to z0. So this is the first main result. I put upstairs here. You can read it. And I remember I will explain just what is omega 0 here. Here, omega 0 is the vorticity profile of the Lamb-Ozane vortex. And this is very simple formula. Omega 0 of psi is equal to 1 over 4 pi e to the minus pi square over k. Let me write also the corresponding velocity field because I will use it. So it's 1 over 2 pi psi per over pi square 1 minus e to the minus pi square over k. It is the Lamb-Ozane vortex, which is the profile of a self-similar solution of the Navier-Stokes equation. Okay? Okay, so what does its theorem here mean? Very simple. It tells you that if the Reynolds number is sufficiently large, yes?
Stupid question. Say, is this thing valid to capital T is equal to?
It's a capital T, okay.
Okay.
The time of existence.
Not related well.
It can be much larger than the T0.
Okay.
Can be, it's as long as you want.
Exactly.
For any fixed time, take it as a multiple of T0, 10 times T0, so you can really see the dynamics. Okay, this is true. Of course, if this capital T becomes very large, these constants here are affected. Okay, this is a result. So there is some proof, and we have to make some compromise of this. So what is the interpretation of this formula? Okay, what happens to your solution? So you have your vorticity in an external field. You start with a Dirac mass. Without the external field, you solve the heat equation, which was mentioned yesterday, because these are radially symmetric initial data. And this gives you as a solution exactly the Ozane vortex, gamma dot nu t, omega 0 of x over square root of nu t. This is what would happen without external field. The theorem tells you that in the real case, what happens is exactly the same, except that the Ozane vortex is advected by the external velocity field, like our material a point vortex. Z prime is f of z of t. This is the ODE given by the external velocity field. If you apply this to the situation where several vortices interact, this gives you rigorous justification of the point vortex system. You start with Dirac masses, you obtain to leading order the point vortex system. So this is extremely simple to see. You have the effect of diffusion, which transform your initial Dirac mass to a self-similar solution with Gaussian profile. And you have the effect of the advection, which is just moving this. And there is no interaction between both effects at this level of approximation. Okay? They just do not interact, we just move. So this is completely natural. And this is the first result. Any question about this statement? There is a lot of we need to say. So let me just say a few comments here. So if you fix gamma Z0 has no influence, but if you fix gamma in the external field, okay, the constant K0 and delta 0 here depends only on the ratio capital T over capital T0, and also on the bounds on the velocity field, of course, they depend on that. So in particular, they are uniform in the Reynolds number as the Reynolds number goes to infinity. So you can take the vanishing viscosity limit here. You can take nu at T fixed, you can take nu to 0, and this tells you that the solution converges to a point vortex which moves along the curve. Okay. So it's absolutely remarkable that we are able to do the vanishing viscosity limit for such singular solutions. Remember, vortex patch, vortex sheets, point vortices in increasing order of singularity. For vortex patches, Navier-Stokes is well posed, Euler is well posed, we can prove the vanishing viscosity limit. For point vortices, this is the result. We go to Euler, except that point vortex is not exactly a solution of Euler, but this is sort of an interpretation of what could be a solution of Euler. In the middle case, vortex sheets, we are not able to handle the vanishing viscosity limit because of all these instabilities. So this is, but in this very singular configuration, we can. Yes?
Just the external depend on the.
Yes?
The rate
Oh, improving you want. So I will be afraid that improve
power.
Okay, so this is in terms of my parameter. Let's look at this beautiful parameter. This is epsilon. This is just the first result so that you don't leave the room immediately. But in fact, I will state the results in 10 minutes where I have epsilon cube here. In fact, this you can increase by making higher order approximate expansion. In fact, the proof is based on the construction of an approximate solution, which can be carried out in principle to arbitrary order. Okay. So this is just the simplest formulation, but replacing this by something more precise is something we can do. This result does not, well, the main drawback of this result, I should make some comments, but I don't know which are the appropriate order. The main drawback of this result is I don't know how to prove it. Don't worry, you can say, I know how to prove this, but I can prove it only as a consequence of a much more complicated result. I don't have any proof that will give this directly. This is so simple. Ozane vortex, this is the heat equation. You move because of the external field. You put two things together, you shake, and they should give this result. I don't know if any. So what exists in the literature, I should get some references. So for both Euler and Navier-Stokes, there was a huge literature showing that if you start with concentrated initial data, you stay concentrated over some time. Okay, so references about concentrated initial data. And here, of course, I have to quote Marquero and Pulvirenti, because they did that starting from the first result, I think, is in 1983 until at least 1993, and this was for Euler. So for Euler, you cannot start with Dirac masses because then it's too singular. So they would start with a well-concentrated vortex blob with some assumptions on it. Depending on which paper you take in the series, the assumptions are more and more relaxed. And they show that you stay concentrated and you are advected by the external velocity. By the way they prove this result is by considering an external field first and then going to the interacting picture. So this is what I do here is really compatible with the style of Marquero and Pulvirenti. These results are very nice in the sense that they consider much more general initial data than just a given Dirac mass. But they are very far of proving something like that. I mean, they just say that you stay concentrated, but they say nothing about the vorticity profile because it's impossible under the assumptions they make. For Navier-Stokes, this is Marquero 1990 and 1998. This is for Navier-Stokes. So for Navier-Stokes, Marquero does not start with point vortices because at that time it was not known that you could start with point vortices, that you have a unique notation. So you would also start with something well concentrated, and then you have two different parameters, the epsilon here and the nu, okay? And he obtains the same kind of results, except that there is some relation between the viscosity and the size of the initial data, which prevents taking the limit of we are considering here, okay? Then there are some other results. There are a recent result by Stefano Cecchi and Christian Zeiss, which is 2022, where they allow for Dirac masses as initial data for Navier-Stokes. But again, they do not prove any profile they do not describe what the solution is really doing. They just say that the solution stays concentrated. The distance of the solution to the Dirac mass in some Wasserstein measure, it stays controlled under the evolution, but it's not a profile. So the only type of work where you have really description of an asymptotic profile is the group in Bath, with Davila, Delfino, Monica Musso, and Junchen Wei. So they have, by gluing methods, they contract solution. They redid the study of the point vortex system, and they impose much stronger assumptions on the initial data, but they are able to prove some profile for Euler. This is not the Gaussian one because they don't like the Gaussian one. They prefer another one, but for Euler, you have the choice. So there are a few results in the literature, but none is describing really the Gaussian profile that you see here starting from initial data. This is it okay? Are you ready for the second version of the theorem? So the second version of the theorem, we'd like to incorporate the deformation of the vortex due to the external field. Remember the pictures I made yesterday? We seen the video that the vortex gets deformed. So we may want to compute this deformation if you want a higher order approximation. But in fact, it's not only because we want to do it. I mean, to prove this, I have to compute the deformation. I do not know how to prove that without computing the deformation. So,
about this higher order.
yes, I was about to write the next order now. So
No. I don't want to go higher. So what's the best rate I can afford for implicit limit when the initial data is good? So suppose the initial data is good, I take the array solutions, I let u go to 0. Isn't it square root of nu the best I can afford or not?
I guess so. I will have to double check, but it's something, yeah.
And then I guess if you don't go to higher order, you stick to this estimate. This is just vorticity net 1 scaling like
yes.
velocity net 2, so square root of nu is enough that you cannot.
Yeah, this is reasonable.
So no assumptions you can put on it.
Yeah, no, if you put assumptions on F, this will not improve this one.
Okay.
Except that is equal to 0 or whatever, in which case we know that this is an exact solution.
Yeah.
But except from that, no, you typically, okay. I will show you how to improve this, but this is by modifying the approximation. Okay. This you can do also for smooth solution. You can compute an asymptotic expansion and then you have a better convergence. But convergence directly to the limiting solution, I suppose square root of nu t is reasonable. Okay, so here I have a raise. So that will become a little bit more complicated, but not too much. I will try to find an ansatz for a different vortex. Okay. So here I compare my solution to a vortex which would be isolated in the environment. There is just the Gaussian one, which is a solution of the Navier-Stokes equation without external field. Now I would like an ansatz for a vortex which fills an external field. So ansatz for a vortex of circulation gamma. Gamma is my circulation, okay, the integral of the vortex. Core size. The core size is square root of nu t because of diffusion, but in the ansatz I will write now, this can be anything. So let me denote L, the core size L, but L you can think of as square root of nu t when you compare with this formula. Position Z in the external field F. Okay, so can we write such an ansatz? Okay, what would be? I mean, suppose we take a snapshot of the video. You see a vortex which is deformed. You say, oh, this is because of the influence of the external field. Can I write an ansatz for the deformation included in elliptical shape, taking into account that it should have circulation L, core size circulation gamma, core size L, position Z, and there should be an external field F. Okay, so this is what we propose. Omega up, depending on gamma, L, Z, F, at point X. This is what I propose. I propose to have this. The first one should be certainly the Rosen vortex, so it's gamma over L omega 0 of X minus C over L. So upon identifying L with square root of nu t, you see that this is exactly this formula here. This is Gaussian vortex located centered at Z with circulation gamma, and this is the square and core size square. So this is the unperturbed vortex. Now, what is the next order term? The next order term is plus W2 of R times A of Z sine 2 theta minus B of Z cosine of 2 theta. I have to explain a little bit these notations, but I still have to see whether this is the correct formula. So what is this R and theta? We introduce the rescale variable sine, which is X minus L over X minus Z, sorry, over L. This is the variable centered at the center of the vortex and rescaled so that the lengths are measured into the unit, natural unit length L. Okay, so this is my side. Okay, okay. And now I introduce polar coordinates for this one. Cos theta R sine theta. So this W2 of R, this is R is just modulus of this, and theta in cos theta sine theta. Theta is the polar angle of this rescale variable. Okay. So the second term in this one. What does A of Z and B of Z? So A of Z, this is 1/2 D1 F1 minus T2 F2 at point Z. Okay. And B of Z is 1/2 D1 F2 plus D2 F1. So A of B measure the deformation due to, these are first order derivatives of F, so this measure exactly the strain rate of the external field. If you give an external field at the point of the vortex, it has some strain, and this strain, what is this? It's related to the symmetric part of the Jacobian matrix, okay? And it's given by these two numbers A and B. Two numbers A and B measure the strain effect of the external field. And this makes that instead of having something really symmetric, because this depends only on modulus of psi, it starts depending on the angle. And then, therefore, if you draw the vortex lines, they are no longer circles, this becomes ellipses. And what is W2 of R? Well, I show you W2 of R. This is R, this is W2, and it's a function which makes something like that. So, of course, it has a definition. It can be obtained by solving some ODE, which I write tomorrow, but not today. Okay? It's something that behaves like a Gaussian. It's order like R squared near the origin. And it's something like R4 e to the minus R squared over 4 at infinity. And it's positive, and it's the only thing we need to know about these guys. Okay? So this is an answer saying that if you put a Gaussian vortex, or it's a Gaussian vortex, because we could take other profiles, but we are married with Gaussian vortex. So you take a Gaussian vortex of circulation gamma, core size L, located at point Z, then under in an external field F, I expect that the vortex profile will be the Gaussian one plus the correction which gives the deformation of the vortex lines to take into account to leading order the action of the external field. So this is just a definition. This is my ansatz, so there is no claim for the moment. The claim comes now. Find an equal version of this result using this ansatz. You see that the difference will be quite spectacular. Okay. So, okay. Theorem 2. I can just copy what is above under the assumptions of theorem 1, under the assumptions of theorem 1, we have so exactly the same hypothesis. There exists positive constants K0, delta 0, and so on, such that the solution, and now I have the better estimate, 1 over gamma, integral over R2, so omega of xt. But now I don't subtract this explicit Lagrangian vortex. I subtract omega. Let me just say I did probably a big mistake. It is not. It's more omega r. Okay. This is for consistency of notation, so I have to do that. So I take my approximate solution with circulation gamma, because the approximate solution should have circulation gamma. The core size L should be replaced by square root of Newton, because this is what the diffusion is doing. Then it should be located at a point Z, which is Z of T, which will satisfy some ODE. And then this should be in an external field, which is F of T at time T, okay? And then X, Dx, and this is less than my constant K0 times epsilon square times epsilon plus delta. I refer to this blackboard for the definition of epsilon and delta. And this is for T also in the same interval. Okay. And now omega r I have defined. It's more complicated, sorry. I mean, it's all this expression here, where you have to substitute L equal to square root of T, and you have to replace Z by some point Z of T, and you have to compute all this A and B using the velocity field at the time, but this is okay. Where Z is the solution of the modified ODE Z prime of T is equal to F of C of T plus mu T Laplacian of F of C of T with initial data C of 0 equal to D0. So this is a better result. It's just an improvement of the previous one. Now I take the same solution, I subtract a better approximation. So the leading term here in my approximation is exactly the Gaussian vortex that you have in theorem 1. To replace L by square root of mu t, so it's gamma over mu t over 0 vortex minus z over square root of mu t. But now I subtracted a more precise correction. And then I see that my remainder is much better. Instead of being epsilon, now it's epsilon cube plus epsilon square delta. Remember that delta is approximately epsilon square. Epsilon is small, so it's epsilon cube, my approximation. So now I have 3 power of square root of mu t. I have epsilon. And you see that you have a modified ODE for the position of the vortex. So this is also affects a little bit the point vortex system by itself. Okay, is there any question so far on this statement? I will finish now only by making comments on that result because we have worked enough for today. Yes.
You approximate the
Yes.
and you estimate the difference between this one and the other one.
Okay, so this is a nice comment, but okay. If I have to explain a little bit what this new system is. I can explain where it comes from, okay? But I will make first the comment that if the velocity, so I have many comments to make. So let's erase this. I keep the physical parameters maybe and erase this. So comments about this modified velocity field or ODE for the position of the vortex. So one remark I should make immediately is that Laplacian of F is gradient pair of V1 F2 minus V2 F1. Maybe it's not the standard way of writing this, but for a divergence-free velocity field, you have this identity. So this is the curve associated with F. So if F is curve-free, is irrotational, for instance, if it's produced by some other vortices which are far away, this term is long. So so in most physical situations I can think of, in fact, this term is not here because it's 0. Okay, so there is not much difference between two equations. But in general, if you give yourself an external velocity field and don't ask how it is produced, you will see that there is a correction here. What is the effect of this correction? Then you have the product. Suppose that I write, okay, I should not use the same letter z of t for both equations, obviously, because they are different. So I should write them to be z tilde or whatever. But anyway, okay, so you have one trajectory of the first. So this is z of t, say, and the other one will diverge. This is the tilde of t, where say that tilde is the second one, okay? The difference between z of t and the tilde of t is all of epsilon square over a reasonable time interval. It depends on the time interval, but it increases exponentially, but it's order of epsilon square because mu t is epsilon square typically. So it's epsilon square times t, because it should be a distance, okay? So this is the order. So the trajectory will diverge like epsilon square. Now, if you compare, so you have a translation here which is not completely correct. You translate by something which is not exactly correct, and this caused something in the error. If you would replace in theorem 1 z by this z, this will improve the error in epsilon square immediately. So this epsilon is something deteriorated because I chose not exactly the right position of the vortex. It should be epsilon square, and this is epsilon cube. Okay, so this is still better, but this should be epsilon square in fact. Okay. And in particular, if Laplacian of f is 0, which is the case in many interesting physical situations, I can write immediately a better estimate here. So that's the first thing I wanted to say. Okay. Any more questions before I make the other comments? Now, if you compute what is the size of this compared to this one, okay? Let me just make this calculation. By the way, why do I write 1 over gamma integral of this? It's because to have something which is dimensionless. I mean, both members of all this inequality are using dimensionless quantity. This is, yes? No, F is a vector field. So Laplacian of F is Laplacian of F1, Laplacian of F2. Do the calculation, you will see that this is an identity. Okay. So this is the case in all this calculation I made for the center of vorticity and so on. I was handling with vector quantities. F is F1, F2. So do the calculation. If it doesn't work, no, but it will work. It will just work. Using the incompressibility condition, of course, you have this identity. Good. Don't hesitate to asking all questions. I mean, I should be able to answer them or not. Okay, so let me just consider in N1 what is the size of both of these terms, just to see how they are comparable. Okay, so the first one, I say 1 over gamma integral over R2 of gamma over L squared omega 0 of x minus z over L dx. Anybody can do the calculation mentally, I suppose. The gamma is gone. You make the change of variable. L square is gone. And then you obtain that this is 1 because the integral of omega 0 is 1. So in the measure I have here, the size of Rosen vortex is 1. Okay. Now, what is the other one? You take 1 over gamma integral over R2 of whatever is here. So W2 of R and then A of Z sine 2 theta minus B of Z cos 2 theta dx. So here writing R was not a brilliant idea because we don't see anything. But remember that this is W2 of x minus z over L in modulus, because this is how the R was defined. So here, if you make an estimate, okay, you have 1 over gamma, you can see. Now, when you integrate W of something over L times dx, it will produce an L square in the same way as here, okay? And now what about this A of Z, whatever? A and B are first case of derivative of the velocity field. But this, by definition, they are bounded by 1 over T0. Okay? So it's 1 over T0. And then you have a constant because you integrate this W2, which is whatever it is. Okay? This gives you, and this is gamma T0 is my D square. So it's constant times L square over T square. But L over D is my aspect ratio. So it's constant times epsilon square. So the first term is 1. The second term is epsilon squared. So here, in this approximation, I neglect the deformation. I reduce the error from epsilon cube to epsilon square. And then this gives theorem 1 up to the mismatch in the definition of D. Okay, so the reason I can have epsilon cube is that I incorporate exactly the epsilon square. So this is the logic. I mean, my expansion, the leading order term is the Gaussian vortex. Then the next correction is order of epsilon square, and then this will be cube, force, and things like that. This is the perturbation expansion. I'll explain tomorrow, okay? When I try to prove this, this theorem. Let me just mention if there was something I wanted to mention. Yes. Okay. So the last thing I will do, I can probably erase this one. We'll try to explain why it's logic to, it's sort of can be expected to obtain this additional term in the position of the vortices. So this is, except for the lack of physical relevance, this is the first viscous correction to the point vortex system. The usual point system, which is just Z prime is equal to F of Z of T, okay? And now they have to leading order a viscous correction, except that it implies the Laplacian, which should be 0 in most of the cases. But this is the first order correction that we have in general. So suppose, assume that you don't like this approximation. I think it's a fair assumption. You probably don't like this approximation. So let's consider only the first one. So assume that omega of xt is equal to exactly gamma over mu t times omega 0, the notion x minus z of t over square root of mu t for some z of t. So suppose that all the higher order correction, order of epsilon square, can be neglected, and I take this as my formula for an approximate vorticity. Suppose that I take this and I compute the center of vorticity. So compute the center of vorticity. So I remember I recall what it is. We did that at the beginning of the lecture. X bar of t is 1 over gamma integral over R2 of x omega of xt dx. But then we can make this calculation, which is completely trivial, but let's do it blindly as if it was something reasonable. Integral over R2. Here you take x is equal to z of t plus square root of mu t times psi to make this change of variable to introduce my rescale variable psi. Okay, so it gives x becomes z of t plus square root of mu t psi. Warning, these are all vectorial quantities. Okay, times omega 0 of psi psi. And now the gamma is gone in this calculation. Where is it gone? This gamma, because 1 over gamma times gamma. So here it's gone, okay? So this is true. And you obtain this, and this becomes exactly z of t. Of course, omega 0 is really symmetric and things like that. So if I know if omega is exactly in this form, z of t is the center of vorticity. Now, let's say x bar prime of t, and I use here exactly the formula I established at the beginning. So it's 1 over gamma integral over R2, and this is an interesting calculation. It's f of xt omega of xt dx. Okay, I do exactly the same change of coordinates, so I obtain integral over R2 times f of z of t plus square root of mu t psi e omega 0 of psi d psi. Okay. And now a Taylor expansion. I make a Taylor expansion of this f. Okay. So you obtain integral of R2, and inside the integral I have f of z of t t plus square root of mu t df of z of t t acting on psi. The first order differential is a linear functional in psi, plus 1/2 mu t d2f of at z of t t acting on psi plus higher order term. I do exactly what our students should not do, and then omega 0 of psi d psi. Okay. And then I make the calculation, knowing that omega 0 is Gaussian. So the first term, the integral is 1. So it's f of z of t t. This term gives 0 because whatever is proportional to psi integrated with respect to omega 0 gives 0. And then you have this. And this is second, okay, this is vectorial again. So I should take this a matrix. Okay, this is a quadratic form in psi, but there are 2 copies of it, one for f1, one for f2. And then you have psi1 square, psi2 square, and psi1, psi2. Psi1, psi2 gives 0, acting on omega 0. Psi1 square and psi2 square give 2, okay, which compensate for the 1/2. So you obtain exactly mu t Laplacian of f of t of t plus higher or plus order of mu t to the power 3/2. And this gives exactly this formula here. So again, if you compute in an external field, this effect is due to the point vortex becoming an Ozane vortex. It's not due to the deformation of the streamlines or whatever. This is an effect due to the finite size of the core. Okay, so it's not so surprising that we obtain this. But again, in most cases, I know this should be 0. I don't know of any physical situation where this f here is non-zero. This Laplacian of f is non-zero, so maybe we should not pay too much attention. Yeah.
And this is also consistent with what Michele was explaining last week. That vortex diagram we have, let's say, the 4th power. So it's this.
Oh yes.
Is it consistent with
It's exactly composed. I mean, it's true that when you take a vortex pair, you see some slowdown of the motion due to the interaction, but it starts at epsilon to the power 4, whereas this is epsilon to the power square. So this term should not be here, absolutely. So you were very paying much attention to both. I think I should stop here because it has been a long lecture already. Questions?
You said you do this couple of times without a great order.
In principle.
But you don't know what that says.
Well, I mean, what we did, okay, there is a constructive procedure, order by order, which can be continued. So in the case of a vortex pair plus and minus, which was explained by Michele Dolce last Friday, we did it to arbitrary order. We showed that recursively, there is no obstacle you can produce. In the general case, we didn't check. There are some, but in principle, you can do it to arbitrary order. Yeah, and obtain an approximate solution, which is more and more precise. So this is just the opportunity for me to say what I will do in the next 2 lectures. Next lecture, I will explain how you construct this approximate solution to the first non-trivial order. So where is the origin of this term? That I will show you. And then, so constructing the approximate solution is interesting because it gives much and more physical information on the solution, because I believe that this approximation, the approximate solution, is really describing what the actual solution is doing. But to finish the proof of theorem 1 or theorem 2, you have to prove that the exact solution stays close of the approximation. And this is a different business. And here we see that if we want to do that, we have to construct the approximation at least at order 4, up to epsilon to the 4. This is the reason why I mentioned that I'm not able to prove theorem 1. With 0th order approximation, I cannot control the remainder. The equation is too singular, so I have to construct a very accurate solution, so that the remainder of this approximation is so small that the singularities of the equation is harmless on it. And this, it's easy to see, we shall see, that you have to construct at least to 4th order. So I did it in the general case, at least to 4th order, because this is a way of closing the argument for theorem 2. Then you can continue to higher orders if you want more precision. But this is a general procedure and there is no obstacle I can see. There is always a way of putting something in the approximate solution so as to and in the work with Michele, we did obtain an error which was much smaller. We are thinking of making e to the minus 1 over epsilon, something like that, but for the moment it's completely open. So this can be probably continued to some other, but for the moment we are already happy to be able to just do it at finite order. Finite order, order 4, is what allows you to go to some non-trivial time. If you do lower order, you go to a time which depends on viscosity and shrink to 0 as the viscosity goes to 0, which is not what you want to do. So you can go to macroscopic time with a 4th order approximation. And I don't know how to shortcut this. I would like, because I'm fed up of computing this approximation. Stupid calculations like that. They are not, they are sort of instructive, they show you. So this I will show also, if you take just the example of a counter-rotating or co-rotating vortex pair, you compute what F is, you compute this quantity, they become very simple, and you take the level set of this approximate solution, you get the deformation of the ellipsis, exactly the picture I've made last time, with the correct alignment of the axis. It is all contained in this solution. This solution, by the way, is well known in the physical literature in connection with what is called the deformed Burgers vortices. There are some kind of explicit solutions of magic flows in a strain field for which asymptotic expansion have been computed, and they agree with this because forward. So this expression is not invented by it's
a concept. Expansion.
Oh yeah, yes. I will send you a very simple expansion, and in the most natural one to do. And the first order you non trivial order to get is this one. You have an expansion, perfectly regular. We have everything now settled to start the expansion. So tomorrow I'll show you what the expansion is, and I try to convince you that the first order you get this, and we even have a formula for it. It's completely a regular expansion. We desingularize the problem by going to self-similar variable, and then it's just an asymptotic expansion like in boundary layer theory when you compute these 4 types of boundary layer. But here it's a very, very simple calculation. Nothing major. Yes.
How much does the order is? I know that they might for if I start with like from that zero.
Yes.
And
so fortunately, if everything goes right, this is what I should explain in the 4th lecture. I will show you that if you start, I have an approximate solution, which is this one, the one that you start with point vortices as initial data. If you start now with a Gaussian vortex, but with small size L here, something like that, after a transient behavior, it converts back to that one. Okay, so this one is a universal model. So if I can make a completely dummy picture, cartoon picture here, you have, okay, I don't define anything. You have the trajectory. This is in the plane. Well, it's not in the plane. It's in some function space. Suppose that this solution depends on time. It's an approximate solution. So it's in a trajectory. You start with an Dirac mass. Here is gamma delta of z0. And in the function space where you realize your solution, it's a trajectory given by this approximate solution. So now you ask me to start with something which is a Gaussian vortex, not very far, but with non-zero. So this one has approximately the same extension as the approximate solution at some given time. So what we show is that very quickly it goes back to that one. And we can measure how far it goes and so on. This is theorem 3. So if you want to see that, you should stay until Thursday. We will prove this one. So this is sort of the well-prepared case is sort of the paradigm or the emblematic case. All solutions converge to it. Okay. The theorem we have a lot of assumptions which are non-optimal, but we show an example of this phenomenon. And this is again documented in the physical literature. If you start with 2 co-rotating vortices, which are Gaussian or Rankine or whatever, they oscillate until they become ellipses. And then they continue like if they started from initial date, from point vortices as initial date. So this is a picture we have in mind. So this is the paradigm of vortex interaction. You should converge to it if you start with slightly perturbed initial data. But first, we have to understand that. And then we can understand more complicated cases.
Okay. So we present GALLAY again. So we start again in 10 minutes, right? By the way, it's redundant to say a finite gradual measure.
Well, in